the universe that surrounds us is often imagined as a serene and silent void, a black canvas scattered with shining stars. Yet when we look closer through the eyes of astronomy, we find that the cosmos is anything but calm. It is a place of violent creation, of explosive death, of light so intense it can overwhelm detectors, and of forces so extreme that human intuition struggles to grasp them. The night sky that appears still is in reality a battlefield of gravity, radiation, and matter, stretching across billions of light years. To tell the story of magnetars, the most magnetic stars in the universe, we must first step back and explore the broader stage on which they exist. Stars are the engines of the universe. They are born from vast clouds of gas and dust, collapsing under the pull of gravity until nuclear fusion ignites at their cores. Fusion is the process that powers every star, from the modest warmth of our sun to the towering brilliance of the most massive giants. Hydrogen nuclei fuse into helium, releasing energy according to the equations of physics first uncovered by scientists in the 20th century. This process continues for millions or even billions of years, depending on the mass of the star. The more massive the star, the faster it burns its fuel and the shorter its life. A star like our Sun will shine for around 10 billion years before gently swelling into a red giant and eventually leaving behind a white dwarf. But the fates of heavier stars are far more dramatic. Stars more than about 8 times the mass of the Sun exhaust their nuclear fuel quickly and cannot hold up against their own gravity when fusion ceases. Their cores collapse in an instant, and the outer layers rebound outward in a titanic explosion known as a supernova. For a brief time, the light of a supernova can outshine an entire galaxy. This single event scatters elements such as carbon, oxygen, silicon, and iron to space, seeding future generations of stars and planets. Without these explosive deaths, the universe would not contain the chemical ingredients necessary for life. It is within these violent endings that neutron stars are born. When the core of a massive star collapses, gravity crushes protons and electrons together to form neutrons. The collapse is halted not by ordinary pressure, but by quantum mechanics, specifically by the Pauli exclusion principle, which states that two identical particles, such as neutrons, cannot occupy the same state. This quantum pressure allows an object with more mass than the Sun to be squeezed into a sphere barely 20 kilometers across. The density of a neutron star is so extreme that a single teaspoon of its material would weigh as much as a mountain on Earth. Neutron stars were first confirmed in 1967, when Jocelyn Bell Burnell detected regular pulses of radio waves coming from deep space. These sources, soon named pulsars, turned out to be rotating neutron stars, whose beams of radiation sweep across Earth like cosmic lighthouses. Since then, astronomers have catalogued thousands of pulsars, each one a rotating neutron star with unique timing and emission properties. Yet not all neutron stars behave the same way. Some do not emit regular pulses, but instead flare with bursts of high-energy radiation. These unusual objects became the first clues that there might exist an even stranger type of star. By the 1970s, scientists began to notice unexplained flashes of gamma rays, the most energetic form of electromagnetic radiation. These bursts were far too powerful to be explained by normal stars or even by typical neutron stars. Among the most famous was the March 5th event of 1979, when detectors recorded an immense burst of gamma rays coming from a source in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. For a fraction of a second, this object released more energy than the Sun produces in thousands of years. The culprit behind such power was not yet understood, but these events hinted that some neutron stars were fundamentally different. Over time, astronomers would identify two distinct classes of peculiar objects: soft gamma repeaters and anomalous X-ray pulsars. Both shared properties that could not be explained by rotation or by ordinary magnetic fields. The only explanation that fit was that these stars were powered by magnetic fields of unprecedented strength. Out of this realization emerged the concept of the magnetar, a neutron star with magnetic fields so intense that they reshape the very fabric of matter and light. The idea that magnetism could dominate the physics of a star opened a new chapter in astrophysics. Our own planet has a magnetic field that protects life from harmful solar radiation, but it is measured in mere Gauss. The magnetic field of a typical refrigerator magnet is only a few hundred Gauss. A neutron star might have a field of 1,000,000,000,000 Gauss. Yet a magnetar surpasses even this, with magnetic fields reaching 10 to the power of 15 Gauss, the strongest in the known universe. To imagine such a field is nearly impossible. It is strong enough to distort the electron clouds in atoms, to bend the paths of photons, and to strain the crust of the star until it cracks in colossal quakes. The discovery of magnetars has reshaped how we think about the extremes of the cosmos. They are rare, with only around 30 confirmed in the Milky Way as of the year 2025. But their influence on astrophysics is immense. Each flare, each pulse, and each storm of radiation they emit pushes the boundaries of what we know about matter and energy. In the vast and violent skies of the universe, magnetars stand as symbols of the power hidden within the smallest and most compact remnants of stellar death. And so, from the quiet light of stars forming in nebulae to the explosive finale of supernovae, we arrive at these exotic objects. Their existence tells us that the universe is not only violent but also profoundly creative, shaping remnants that challenge the laws of physics themselves. As we move deeper into their story, the question becomes clear. What are these compact stars with magnetic fields so powerful they push the laws of physics to the limit? The story of the violent skies does not end with the birth of neutron stars. To understand why they matter, we must widen our gaze to the forces that sculpt the universe itself. Gravity, the most ancient of cosmic powers, is the architect of every structure in space. It is gravity that gathers hydrogen into clouds, ignites stars, and brings them to their fiery deaths. Yet gravity alone cannot explain everything. When stars collapse into neutron stars, the struggle between gravity and quantum mechanics produces some of the strangest objects we can study. These objects become laboratories where nature conducts experiments, far beyond anything possible on Earth. When a massive star collapses in a supernova, the violence does not simply destroy, it also creates. The outer layers hurled into space enrich the surrounding galaxy with heavy elements. The oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged in such explosions. Each neutron star, each pulsar, and each magnetar is the remnant of a stellar death that helped make life possible. In this sense, the violent skies are not only destructive, but also generative. They ensure that galaxies evolve, that planets form, and that complexity arises from chaos. By the mid-20th century, scientists began to realize that studying neutron stars was not only about cataloging odd celestial objects. These dense remnants offered windows into the behavior of matter under pressures and densities unimaginable on Earth. Inside a neutron star, matter is squeezed to densities greater than an atomic nucleus. The entire star, only 20 kilometers across, contains mass comparable to that of the Sunday. If one were to drop an object from a mere meter above the surface, it would strike the crust at a fraction of the speed of light. The gravitational pull is so strong that escaping requires speeds close to half the speed of light. The detection of pulsars in 1967 was the first breakthrough. Jocelyn Bell Burnell and Anthony Hewish found a source emitting radio pulses with astonishing regularity. At first, some speculated these signals might even be artificial, earning the nickname LGM for Little Green Men. But soon it became clear they were the natural signatures of rotating neutron stars. Each rotation, each beam sweeping across Earth, was a cosmic clock, ticking with a precision that rivaled the best instruments built by humans. These discoveries confirmed the existence of neutron stars and opened a new era of astrophysics. Yet, in this triumph of discovery, anomalies began to appear. Some neutron stars did not fit the expected patterns. They were too bright in X-rays, too erratic in their emissions, or prone to bursts of gamma rays. far beyond what rotation could explain. These objects confounded astronomers, hinting at hidden sources of power. Over the following decades, observations from satellites like the Vela detectors, and later from missions such as Rossi, X-ray Timing Explorer, SWIFT, and Fermi, revealed that these sources were distinct from ordinary pulsars. Their energy was not derived from rotation or accretion, but from something far stranger. The key to their behavior lay in magnetism. Magnetism on Earth is familiar in everyday ways. It guides compasses, drives electric motors, and shields us from solar wind. The magnetic field of Earth measures around half a Gauss. A laboratory magnet might reach thousands of Gauss. A neutron star has fields in the trillions of Gauss. But magnetars are in another league altogether, reaching 10 to the power of 15 Gauss. In such fields, the very structure of atoms is distorted. Electrons are forced into narrow cylinders along magnetic lines. Photons themselves behave differently, splitting or altering their paths, a phenomenon called vacuum birefringence, predicted by quantum electrodynamics. This revelation reframed our understanding of stellar remnants. Instead of being powered by spin, magnetars shine by the decay of their colossal magnetic fields. Over tens of thousands of years, these fields unwind and release energy, cracking the crust of the star, sending bursts of X-rays and gamma rays across space. These events are so powerful that they can affect planets many light years away. The March 5, 1979, burst from the Large Magellanic Cloud was a wake-up call. It showed that cosmic events could be felt across vast distances, even influencing detectors orbiting Earth. The violent skies, then, are not abstract. They interact with our own planet. When a giant flare erupted from SGR 1806-20 in December 2004, the blast briefly altered Earth's ionosphere. The event was nearly 50,000 light-years away, yet still powerful enough to leave its mark here. Had it occurred closer, within a few dozen light-years, it might have damaged satellites or disrupted radio communication on a global scale. Though Earth is safe from such near catastrophes due to the rarity of nearby magnetars, the lesson is clear. The universe is not distant and disconnected. Its violence echoes across the void. These revelations set the stage for one of the most important questions in modern astrophysics. How does such extreme magnetism arise? And what can it teach us about the laws of physics? Magnetars stand as natural particle accelerators, quantum laboratories, and cosmic lighthouses, all compressed into spheres only a few dozen kilometers wide. Their existence challenges us to rethink our assumptions and pushes us toward deeper questions about matter, energy, and the fate of stars. The violent universe is not only revealed through spectacular explosions or extreme magnetic storms, but also through the quiet persistence of time itself. When we look up at the night sky, we see light that has traveled for thousands or millions of years before reaching Earth. Every photon is a messenger, carrying the memory of an event that happened long ago. Some of these photons come from stars like our Sun, still burning steadily. Others come from stars that have already died, their light only now finishing its journey across space. In this sense, the night sky is both a map and a history, showing us a universe in constant upheaval. The story of neutron stars and magnetars is one of survival after destruction. A massive star that collapses and explodes has, in one sense, ended its existence. Yet its core, crushed into a sphere only a few dozen kilometers wide, remains as a fossil of that violent process. The surface of such a star is unlike anything we can imagine. A thin crust of ions and electrons, harder than any material on Earth, floats above an ocean of neutrons, so dense that the very idea of solid or liquid becomes meaningless. Beneath lies a core where the physics of matter is pushed to limits we cannot reproduce in any laboratory. Some theories suggest that exotic states of matter, perhaps quark matter or hyperons, might exist there, But these remain open questions, waiting for observation to confirm. What we do know is that neutron stars are stable only because of quantum mechanics, the Pauli exclusion principle that prevents neutrons from occupying the same state resists further collapse. Were it not for this principle, many of these objects would fall inward until they became black holes, objects from which not even light can escape. That razor edge between a neutron star and a black hole is one of the most fascinating thresholds in astrophysics. Magnetars live on that edge, reminding us of how thin the line can be between stability and total collapse. The diversity of neutron stars also reveals the creativity of the cosmos. Some spin hundreds of times per second, producing radio pulses that sweep across Earth like the ticking of a clock. Others are dim and quiet, detectable only through faint X-rays. And then there are the magnetars, unpredictable and explosive, prone to outbursts of radiation that dwarf any other neutron star phenomenon. Together, they form a family of stellar remnants that allow us to probe questions about gravity, nuclear physics, and magnetic fields at scales impossible to achieve elsewhere. Humanity's role in this story is not passive. For centuries, we looked at the night sky with naked eyes, seeing patterns and myths. But with radio telescopes, X-ray observatories, and gamma-ray detectors, we now study the universe across the full spectrum of light. Each instrument has pulled back another veil. The discovery of pulsars in the 1960s, the detection of gamma-ray bursts in the 1970s, the classification of magnetars in the 1990s, all represent milestones in our expanding understanding. These advances remind us that the violent skies are not beyond comprehension. With patient observation and careful analysis, we can interpret the signals carried by light across unimaginable distances. And yet, even with this progress, mysteries remain. We know that magnetars exist, but we still ask how they acquire such immense magnetic fields. We know they erupt in giant flares, but we still struggle to predict when or why. We know they are rare, but we cannot yet say how many may be hidden across the Milky Way, waiting to flare and reveal themselves. These unanswered questions are what drive science forward. The violent skies are not only a stage for stars, but also a stage for human curiosity. Each burst and each pulse challenges us to refine our theories and improve our instruments. From a broader perspective, the study of violent astrophysical events also reshapes how we think about our place in the cosmos. Earth orbits a stable, middle-aged star in a relatively quiet corner of the Milky Way. We are fortunate that our sun does not have the mass to become a supernova, nor will it collapse into a neutron star or magnetar. Yet the elements that make life possible on our planet came from the deaths of such stars long ago. Our bones, our blood, and the very air we breathe carry the legacy of ancient supernovae. In this sense, the violence of the universe is not distant. It is inside us. We are built from the ashes of exploding stars. To grasp the scale of this connection is to recognize that life is a product of both creation and destruction. The calmness of our sky hides the fact that elsewhere in the galaxy, stars are being born, burning, collapsing, and exploding at this very moment. Neutron stars are forming, pulsars are ticking, magnetars are flaring. The universe is alive with violence and energy, and we are both observers and participants. Our existence depends on the cycles of birth and death that govern the cosmos. This is why the study of magnetars, though seemingly obscure, is profoundly meaningful. They are not just rare curiosities catalogued by astronomers. They are expressions of the same physical laws that govern every atom in our bodies. They are the ultimate demonstration of how matter and energy behave under conditions far beyond Earth. By studying them, we learn not only about the stars, but also about the universe itself, about its capacity for violence, its creativity, and its boundless extremes. And so, Chapter 1 closes with a realization. The universe is not empty or quiet. It is filled with storms of radiation, explosions of matter, and stars transformed into remnants so dense and powerful that they redefine the limits of physics. Among these remnants, magnetars stand out as the most dangerous, the most magnetic, and the most extraordinary. What we have seen so far is only a beginning. In the chapters ahead, we will follow the journey from the collapse of massive stars to the birth of neutron stars, and finally to the emergence of magnetars. The question that now rises is simple and profound. What forces shape these compact stars into objects whose magnetic fields stretch the laws of nature to their breaking point? The story of every neutron star begins with a massive star that has burned through its life at a furious pace. Unlike our Sun, which will live for billions of years, these giants live fast and die young. A star more than 8 times the mass of the Sun exhausts its nuclear fuel in only a few million years. Its core blazes with fusion, transforming hydrogen into helium, helium into carbon and oxygen, and finally heavier elements such as silicon and iron. Each stage burns faster than the one before, like a candle racing toward its end. When iron builds up in the core, the star reaches a critical limit. Iron cannot release energy through fusion, and without new energy to support it, the balance between pressure and gravity collapses. The collapse happens with breathtaking speed. In less than a second, the core of the star implodes. Protons and electrons are forced together into neutrons, releasing a flood of neutrinos in the process. The densities reached in this collapse exceed anything outside of a black hole. Matter falls inward until it is stopped by neutron degeneracy pressure, the quantum mechanical effect that arises because neutrons cannot occupy the same state. At this moment, the core stabilizes into what will become a neutron star. The outer layers, still falling inward, crash against this suddenly rigid core. The rebound drives a shockwave outward, and with the help of neutrino energy, the entire star detonates as a supernova. For a brief time, the brilliance of the explosion rivals that of a galaxy. The Crab Nebula, in the constellation Taurus, is a remnant of such a blast recorded on Earth. In the year 1054, ancient astronomers saw a new star appear in the sky brighter than Venus, visible in daylight for weeks. What they could not have known is that at the heart of the expanding nebula lies a neutron star, spinning 30 times each second, sending pulses of radiation across space. This pulsar is the living core of a star that died nearly 1,000 years ago, still shining in its transformed state. Supernovae are not only spectacular, they are essential. In these explosions, elements heavier than iron are forged in the intense flux of neutrons, a process called rapid neutron capture. Gold, uranium, and other heavy elements scattered across the cosmos are born in such moments. When the blast expands into space, it enriches surrounding clouds with these ingredients. From those clouds, new stars and planets eventually form. Our own Earth is rich with metals that once lay in the heart of long-dead stars. Without supernovae, the universe would be a barren expanse of hydrogen and helium, devoid of the chemical diversity required for life. The formation of a neutron star within this chaos is an act of both destruction and creation. Imagine a sphere with the mass of the Sun, compressed into a diameter of only 20 kilometers. The density of such an object is so great that a single teaspoon of neutron star matter weighs billions of tons. The surface gravity is nearly 200 billion times that of Earth. To stand on such a surface, if one could survive, would mean being crushed instantly. Yet this extreme state of matter is real, a consequence of the most violent process nature can provide: the death of a massive star. In this transformation lies one of the universe's greatest paradoxes. Out of death comes a new form of existence. The star has died, yet something remains. It is no longer a burning sphere of gas, but a solid remnant, governed by quantum mechanics and relativity. The neutron star becomes a beacon, whether through the steady ticking of radio pulses or through eruptions of radiation. These remnants connect us to the life cycles of galaxies, the recycling of matter, and the ongoing evolution of the cosmos. The physics of this birth is staggering. As the core collapses, angular momentum is conserved, and the star's rotation speeds up dramatically. Just as a skater spins faster when pulling in their arms, the collapsing core spins hundreds of times per second. Magnetic fields trapped in the plasma of the star are also compressed and amplified. In some cases, they reach unimaginable strengths. This is the seed of a magnetar. In rare stars, the combination of rapid rotation and convective motion during collapse drives a dynamo effect that boosts the magnetic field to levels 1 trillion times stronger than those on Earth. When such a field is locked into the newborn neutron star, a magnetar is born. Yet not every supernova yields such an extreme remnant. Most produce ordinary neutron stars, or black holes. Whether a star becomes one or the other depends on subtle details: the mass of the progenitor, the symmetry of the collapse, and the efficiency of neutrino heating. These details are the subject of intense study, for within them lies the answer to how magnetars come to exist at all. Observations of supernova remnants, combined with simulations of stellar collapse, continue to refine our understanding. But already the picture is clear. Among the ruins of massive stars, neutron stars emerge, and among them, the rarest of all are magnetars, whose magnetic fields push the laws of physics to their edge. The path from star to supernova to neutron star is thus a journey of transformation, a cycle that enriches the cosmos, even as it destroys. It is a story written into the very atoms of our bodies and echoed in the remnants scattered across the galaxy. And it is the beginning of the story of magnetars, those extraordinary stars that emerge only from the most violent deaths. The moment a massive star collapses is both a catastrophe and a revelation. To understand what is truly happening inside, we must imagine physics under conditions far beyond anything ever achieved in laboratories on Earth. The collapsing core of a star is initially supported by electron degeneracy pressure, the same effect that stabilizes white dwarfs. In a white dwarf, electrons resist being packed too tightly because the Pauli exclusion principle forbids them from sharing the same state. But when the mass of the collapsing core exceeds the Chandrasekhar limit of about 1.4 solar masses, this pressure is no longer enough. Electrons are forced into protons, creating neutrons and neutrinos. The flood of neutrinos is staggering. In the first second of collapse, the star emits more energy in neutrinos than our Sun will release in its entire 10 billion year lifetime. These ghostly particles, almost massless and nearly impossible to detect, carry away the bulk of the energy of the explosion. Only a tiny fraction of their power helps revive the stalled shockwave that blasts the outer layers into space. Without the contribution of neutrinos, the collapse would simply form a black hole without the fireworks of a supernova. The discovery of neutrinos from supernova 1987A, detected in underground detectors in Japan and the United States, confirmed this picture. Those fleeting signals, only a handful of events recorded, told us that the models were correct. Supernovae are neutrino engines, as much as they are explosions of light. What remains after the blast is a neutron star, spinning and magnetic, compact and enduring. The rotation of such an object is breathtaking. A core that once rotated perhaps once every few days now rotates many times per second. Some neutron stars spin so rapidly that their beams of radio emission sweep Earth hundreds of times each second. These millisecond pulsars are among the most precise natural clocks in the universe, their timing so accurate that they rival atomic clocks. Others rotate more slowly, but even a neutron star that turns once per second carries rotational energy far greater than the total energy output of our Sunday. This rotational power, however, is not eternal. Neutron stars lose energy through magnetic braking, gradually slowing down as they emit radiation. The strength of their magnetic fields determines how quickly this happens. Ordinary pulsars may shine for millions of years before fading into invisibility, but for a rare few, the magnetic fields are so intense that they dominate the life of the star. These are the magnetars, whose fields decay on timescales of only 10,000 to 100,000 years, a blink of an eye in cosmic terms. Their lives are short, violent, and unforgettable. The diversity of remnants reminds us that the universe does not follow a single script. Some collapsing stars vanish into black holes, their cores crushed beyond return. Others stabilize as neutron stars, radiating as pulsars or cooling in quiet isolation. A smaller fraction become magnetars, whose bursts of energy remind us of the raw force contained in magnetic fields. The key differences are found in the fine details of collapse: the spin rate, the internal convection, and the seed fields inherited from the progenitor star. Simulations of core collapse supernovae suggest that if the proto-neutron star spins fast enough, magnetic dynamos can amplify fields by orders of magnitude. This is the path to magnetar birth. The environment surrounding a newborn neutron star is also shaped by the explosion. Supernova remnants, vast clouds of expanding gas, provide laboratories for study centuries after the event. The Crab Nebula, Cassiopeia A, and Supernova 1987A each reveal different stages of this evolution. By studying the shape, speed, and composition of these remnants, astronomers piece together the hidden processes of collapse. Within them, we sometimes detect the compact object left behind, spinning or flaring, proving that the violent death of a star is not the end but the beginning of something new. The balance of forces inside a neutron star is exquisite. Gravity pulls inward with nearly unimaginable strength. Neutron degeneracy pushes back. The result is an object so compact that space and time themselves are distorted. Relativity predicts that clocks run more slowly near its surface compared to clocks on Earth. Light emitted from the surface is gravitationally redshifted, stretched to longer wavelengths as it escapes the deep potential well. These effects are not theoretical abstractions. They have been measured by X-ray telescopes observing emission from neutron star surfaces, confirming that Einstein's predictions hold true under the most extreme conditions. Each neutron star is thus a meeting point of physics at its most fundamental. Quantum mechanics, relativity, nuclear physics, and plasma dynamics all collide within its 20-kilometer radius. For scientists, this makes them priceless laboratories. For the universe, they are necessary outcomes of the cycle of stars. And for us, they are reminders that even in destruction, there is continuity. The death of one star seeds the birth of others, and the remains of that death become markers of cosmic history. In this way, the transformation from supernova to neutron star is not just a violent end, but also a rebirth. The ashes of the star spread through space to form the building blocks of planets and life, while the collapsed core continues to shine, pulse, or flare for thousands of years. The cycle is relentless, and through it, the universe sustains its creativity. Each neutron star, each magnetar, is a relic of this process, carrying within it the story of the collapse that created it. The birth of a neutron star is one of the rare moments when the entire balance of a star is rewritten in the blink of an eye. To grasp the magnitude of this transformation, we must remember what has been lost and what has been gained. A giant star that once shone with brilliance, holding entire planetary systems in its grip, vanishes in a heartbeat. Yet in that collapse, matter is driven into a state that does not exist anywhere else in nature. The neutron star is the residue of billions of years of stellar fusion, compressed into a volume no larger than a city. The fact that such an object can exist at all is one of the universe's most astonishing revelations. The journey from supernova to neutron star is also a journey of energy. When a star explodes, its outer layers are blasted outward at thousands of kilometers per second, carving shock waves into the surrounding medium. These shock waves stir up cosmic rays, high-energy particles, that travel across the galaxy and eventually strike Earth's atmosphere. In this way, the death of a single star can influence the entire galaxy, from the growth of nebulae to the chemistry of new solar systems. Meanwhile, the compact core left behind becomes a reservoir of concentrated physics, a stable remnant broadcasting radiation across the spectrum. The Crab pulsar, at the heart of the Crab Nebula, is a striking example. Nearly 1,000 years after its birth, it continues to spin 30 times each second, sending pulses of radio waves, X-rays, and gamma rays across space. Its light has been detected by telescopes across the electromagnetic spectrum, providing one of the most complete portraits of a neutron star ever assembled. Through the Crab pulsar, we see the enduring link between a supernova's violent death and the quiet persistence of its remnant. Other examples, like Cassiopeia A, show younger remnants where shock waves are still unfolding. In every case, the compact object at the center is the key to unlocking the history of the explosion. Magnetars add a new dimension to this story. Their birth is similar to that of other neutron stars, yet the outcome is far more dramatic. In the moments after collapse, rapid rotation and turbulent convection amplify magnetic fields to levels no laboratory on Earth could ever hope to reproduce. The fields become frozen into the star as it stabilizes, storing colossal amounts of energy. Unlike ordinary pulsars, whose power comes mainly from rotation, magnetars radiate by releasing this magnetic energy. Over time, their fields twist and decay, cracking the crust of the star and producing bursts of radiation that can be seen across the galaxy. This path from supernova to neutron star is thus not a single line but a branching road. Some stars collapse into black holes, where the core is crushed beyond visibility. Others stabilize as pulsars, slowly spinning down over millions of years. A few, under the right conditions, become magnetars, whose short lives are marked by bursts of intensity that outshine entire galaxies. Each path is dictated by the interplay of mass, spin, magnetism, and the chaotic details of collapse. It is a reminder that the universe is not governed by simplicity, but by complexity, producing a rich diversity of outcomes from the same basic laws. For humanity, these objects are more than curiosities. They challenge us to think about matter at its most extreme. What happens when protons and electrons merge? How do neutrons behave when pressed into densities greater than atomic nuclei? Do exotic states of matter emerge, such as quark matter or hyperons? Observations of neutron stars and magnetars offer the only window into these questions. Each pulse, each flare, each spectrum recorded by telescopes carries clues to the physics of matter beyond the reach of particle accelerators on Earth. The transformation also forces us to reflect on the fragile balance of life in the universe. Supernovae are destructive on local scales, yet without them there would be no planets, no chemistry, no biology. The same explosions that destroy stars also sow the seeds of life. The compact remnants, though dangerous in their bursts of radiation, help us refine our theories of relativity and quantum mechanics. They are both destroyers and teachers, both cosmic hazards and cosmic gifts. By the end of this journey, we see that the path from supernova to neutron star is one of the defining processes of the cosmos. It is through this path that galaxies are enriched, that life becomes possible, and that the extremes of physics are revealed. The rare emergence of magnetars from this process shows us that even within the narrow confines of stellar death, the universe can create objects of unparalleled strangeness. And so, Chapter 2 closes with a simple truth. Out of fire and collapse, out of destruction and loss, comes a new form of existence. The neutron star, and especially the magnetar, is not just a remnant of a dead star. It is a signpost pointing toward the extremes of nature. In the chapters ahead, we will step closer to these rare objects themselves, examining their unique properties and the forces that make them the most magnetic stars in the universe. Among all the stellar remnants scattered across the galaxy, magnetars stand out as the rarest and most extreme. They are neutron stars, yet their properties push them far beyond what was once thought possible for such objects. To understand them, we must place them in context. Neutron stars are already extraordinary, containing more mass than the Sun in a sphere no wider than a city. Their densities reach values so high that the word dense begins to lose meaning. But magnetars go further, defined not only by their compactness, but by magnetic fields of unimaginable strength. They are the most magnetic objects known in the universe. The concept of a magnetic field is familiar in everyday life. Compasses point north because Earth has a global magnetic field. This field is about half a Gauss in strength, enough to guide navigation and shield us from cosmic rays, but far too weak to affect the structure of matter. In laboratories, scientists can create magnets of several thousand Gauss, and in rare cases, up to tens of millions of Gauss for experiments. Ordinary neutron stars have fields of 1 trillion Gauss, but magnetars rise above them all, with fields reaching 10 to the power of 15 Gauss. This means their magnetism is 1 million times stronger than that of ordinary neutron stars and 1 quadrillion times stronger than Earth's. In such fields, the familiar rules of matter begin to break. Electrons are forced into narrow orbits aligned with the field, atoms become elongated, and the very fabric of quantum electrodynamics reveals new phenomena. Vacuum birefringence, a prediction of quantum theory, occurs when empty space itself behaves like a prism, splitting light depending on its polarization. Photons that would normally pass unaffected instead change their paths in the presence of such extreme magnetism. These effects are not science fiction, but measurable consequences of fields so strong that they redefine the behavior of space itself. Physically, a magnetar does not look outwardly different from other neutron stars. Its radius is about 20 kilometers, its mass around 1.5 times that of the Sun, and its density billions of tons per cubic centimeter. If one could somehow scoop a spoonful of magnetar matter, it would outweigh mountains. Yet the difference lies in the invisible power of its magnetism. This hidden energy dominates its life. While pulsars shine primarily because of their rotation, and some neutron stars feed on gas from companion stars, magnetars glow by converting magnetic energy into heat and radiation. Over tens of thousands of years, these fields decay, cracking the crust, releasing bursts of X-rays and gamma rays, and making magnetars some of the most unpredictable objects in the sky. Their rarity makes them even more intriguing. As of the year 2025, astronomers have confirmed about 30 magnetars in the Milky Way. Compared to the thousands of pulsars and billions of ordinary stars, this is a tiny fraction. Yet despite their small number, they have drawn immense attention. Each magnetar is a natural experiment, showing us what matter and energy can do when pushed to limits unreachable elsewhere. They are like cosmic laboratories, testing theories of nuclear physics, relativity, and quantum electrodynamics. The decay of their magnetic fields provides a unique source of power. When the field lines twist and rearrange, they induce stress in the star's crust. The crust, though only a kilometer thick, is rigid enough to resist at first, but eventually it fractures in what scientists call starquakes. These quakes release energy as bursts of radiation, sometimes lasting only fractions of a second, but releasing as much energy as the Sun emits in 100,000 years. The bursts can repeat, giving rise to the name soft gamma repeaters. In extreme cases, giant flares can outshine all other X-ray sources in the galaxy. The study of magnetars has changed how we think about stellar remnants. They demonstrate that magnetic fields are not a secondary detail, but a central force shaping the lives of stars after death. They also show that the universe is more creative than once imagined, producing not just neutron stars and black holes, but a spectrum of exotic remnants that challenge our understanding of physics. In the next steps of their story, we will see how their existence was uncovered through sudden bursts of radiation, and how each flare brought us closer to grasping their true nature. The power of a magnetar lies in more than numbers written in equations. To imagine 10 to the power of 15 Gauss is to imagine a force so intense that it reshapes the very atoms we take for granted. On Earth, an atom of hydrogen has a spherical cloud of electrons orbiting its proton. In the presence of a magnetar's field, that sphere is stretched into a needle, electrons forced into narrow tracks along magnetic lines. Chemistry as we know it ceases to exist. Bonds that define molecules are torn apart. Even the idea of solid matter, built on stable arrangements of atoms, begins to collapse under the weight of such magnetism. This environment is so far from human experience that it becomes difficult to picture. Yet by measuring the radiation from magnetars, scientists have been able to infer these effects. In 2017, astronomers using the European Southern Observatory's Very Large Telescope found evidence of vacuum birefringence near a neutron star, a sign that quantum electrodynamics was playing out in the open sky. Though the measurement was not directly from a magnetar, it confirmed that strong magnetic fields affect light itself, as predicted. Observing a magnetar is to witness physics at the boundary of theory and reality. What makes magnetars especially fascinating is that they live fast and die young. While pulsars can survive for millions of years, the extreme magnetic fields of magnetars decay within only tens of thousands of years. This decay heats the star, powering persistent X-ray emission, even when no bursts are occurring. The magnetic field unwinds like a coiled spring, releasing energy that cracks the crust and shakes the star. These violent episodes reveal themselves as flares, sometimes brief flashes, and sometimes giant outbursts that briefly outshine entire galaxies. After each flare, the magnetar calms for a time, only to flare again when stresses rebuild. The crust of a magnetar is one of the strongest materials known in the universe, yet even it cannot withstand infinite pressure. Models suggest that the breaking strain of the crust is about 10 billion times that of steel. When it fractures in a starquake, seismic waves ripple through the 20-kilometer sphere, producing oscillations that can modulate the radiation we see. In this way, studying the vibrations of magnetar flares is like listening to the ringing of a cosmic bell, giving clues about the interior structure of the star. It is seismology on a stellar scale, helping astronomers probe depths hidden beneath a crust thicker than mountains. Despite their violence, magnetars are rare jewels hidden within the Milky Way. Only around 30 have been confirmed, with perhaps several hundred more waiting to be discovered. They are not scattered evenly, but often found in regions where massive stars are born and die, such as near star-forming nebulae. This makes sense, since magnetars are the children of massive stars whose short lives end in collapse. By mapping magnetar locations, astronomers also trace the geography of stellar birth and death across the galaxy. These numbers may seem small, yet their significance is vast. A single giant flare from a magnetar can alter the space environment of Earth, even across tens of thousands of light years. The December 2004 flare from SGR 1806-20 was so powerful that satellites recorded it despite its enormous distance. For a brief moment, it was the brightest source of gamma rays ever seen from beyond our solar system. That a star could produce such a signal across half the galaxy reminds us of the scale of their energy. The lives of magnetars are short on cosmic timescales, but their impact lasts far longer. The fields that define them eventually decay, their outbursts fade, and they transition into quieter neutron stars. Yet their flares leave trails of energy, their remnants linger in supernova shells, and their existence influences the evolution of galaxies. Each magnetar is thus a fleeting but powerful actor on the stage of the universe. A reminder that rarity does not mean insignificance. Their nature forces us to confront questions of fundamental physics. How do such intense magnetic fields form in the first place? What precise conditions during collapse lead to a magnetar instead of an ordinary pulsar? How does magnetic decay proceed within matter so dense that it challenges every model of nuclear physics? These are not just details of stellar astronomy. They are tests of physics at scales we cannot reach otherwise. In studying magnetars, scientists probe the intersection of relativity, quantum theory, and plasma dynamics. They are, quite literally, laboratories of the impossible. And so, The nature of magnetars reveals itself not only through their numbers or their rarity, but through the unique window they open. They show us atoms torn apart, crusts breaking under stresses beyond imagination, and light itself bending to magnetic will. Each observation brings us closer to understanding, yet also raises deeper questions about what matter and energy can do. When we step back and think about the family of neutron stars, magnetars appear like the fiery prodigies among their kin. Ordinary pulsars spin with clock-like precision, some for millions of years. Others fade into invisibility, cooling quietly in the dark. But magnetars are restless, unpredictable, and short-lived. Their lives may last only 10,000 to 100,000 years, yet in that span they leave marks across the galaxy that astronomers can detect even from tens of thousands of light-years away. Their rarity makes them difficult to study, but the violence of their outbursts ensures they cannot go unnoticed for long. The most extraordinary of these outbursts are giant flares. In December 2004, the magnetar known as SGR 1806-20 erupted with such force that it briefly saturated detectors across the solar system. The flare began with a spike of gamma rays so intense it altered Earth's ionosphere, despite coming from nearly 50,000 light-years away. The energy released in less than a second equaled the total output of the Sun over hundreds of thousands of years. No other type of stellar remnant is known to produce such cataclysmic bursts. They reveal the magnetic heart of magnetars, a source of power that dwarfs every other engine, except black holes themselves. Yet between these titanic eruptions, magnetars can also produce smaller, more frequent bursts of X-rays and gamma rays. These episodes, sometimes lasting only milliseconds, are thought to result from local fractures in the crust or rearrangements of magnetic fields. The variability of these signals makes magnetars difficult to predict. Unlike pulsars, which rotate with regularity, magnetars behave more like seismic planets, cracking and flaring when stresses build. This unpredictability is both a challenge and an opportunity. Each flare provides a sudden experiment, a natural test of physics at extremes. In addition to bursts, magnetars also emit persistent X-rays powered by the decay of their magnetic fields. This constant emission allows astronomers to detect them, even when they are quiet. The spectra of these X-rays carry information about the temperature of the surface and the processes occurring in the magnetosphere, the region of space dominated by their magnetic fields. By comparing these emissions to models, scientists refine their understanding of how magnetic energy dissipates over time. In this sense, even the silence of a magnetar speaks volumes, as the faint glow of its surface encodes the history of its decaying field. As observations accumulate, patterns emerge. Magnetars are often found in star-forming regions of the galaxy, consistent with their origin from massive stars. Many lie near supernova remnants, confirming their youth. Some show links to fast radio bursts, mysterious flashes of radio waves first discovered in 2007. In 2020, astronomers observed a magnetar in our own galaxy, SGR 1935+2154, producing a fast radio burst, cementing the connection between the two phenomena. Though not all fast radio bursts may come from magnetars, this event demonstrated that at least some do. This discovery tied together two of the most puzzling phenomena in modern astronomy, showing once again that magnetars are key players on the stage of cosmic extremes. Despite all we have learned, many mysteries remain. Do magnetars evolve into ordinary pulsars once their magnetic fields decay? Or do they fade into invisibility, leaving only cooling neutron stars behind? How many magnetars remain undiscovered in the Milky Way? Too distant or too faint for current instruments to detect? What role do they play in shaping the interstellar medium, with their bursts and flares injecting energy into surrounding space? These questions drive research, and upcoming observatories promise to provide new answers. But for now, each magnetar we study is a singular opportunity, a chance to watch physics unfold at its outermost edge. The nature of magnetars, then, is to embody extremes. They are small in number, but vast in impact. They live short lives, yet burn with power greater than whole galaxies. They challenge our theories while illuminating the universe with signals no one can ignore. By studying them, we confront the boundaries of knowledge, from quantum mechanics to relativity, from the smallest particles to the largest scales. They remind us that the universe does not lack imagination. Out of the collapse of stars, it has created objects whose very existence stretches our understanding of what matter and energy can do. And so Chapter 3 closes with magnetars firmly established in our minds not as curiosities but as central figures in the story of the cosmos. They are neutron stars, yes, but they are neutron stars transformed, magnified by magnetism to become the most dangerous and fascinating stars in existence. In the next stage of the story, we will follow the path of discovery itself, tracing how astronomers came to recognize these hidden giants through bursts of gamma rays and X-rays that carried their signatures across the galaxy. The discovery of magnetars did not arrive through calm observation, but through sudden and violent interruptions in the sky. For decades after the first pulsar was identified in 1967, astronomers thought they understood neutron stars as rotating lighthouses, powered by spin and emitting beams of radio waves. But the universe had another story waiting, and it was written in bursts of gamma rays and X-rays so intense that they startled the detectors that first caught them. These bursts did not fit the rhythm of pulsars, nor did they resemble the steady glow of ordinary stars. They were sudden, explosive, and mysterious, demanding explanations that would eventually lead to the recognition of magnetars. The first great clue came on March 5, 1979. Instruments aboard satellites recorded an immense flash of gamma rays from the direction of the Large Magellanic Cloud, a small galaxy orbiting the Milky Way. In less than a fraction of a second, the burst released more energy than the Sun emits in thousands of years. Detectors that had been designed to watch for nuclear tests on Earth were overwhelmed by the intensity of the signal. The event, now known as the March 5th flare, marked the first detection of what would later be called a giant flare. The source was eventually identified as SGR 0525-66, a soft gamma repeater that revealed itself as a new kind of celestial object. This was not the only time satellites built for earthly purposes made cosmic discoveries. The Vela satellites, launched by the United States to monitor compliance with nuclear test ban treaties, frequently picked up bursts of gamma rays from beyond Earth. At first, scientists debated whether these signals came from the Sun, distant galaxies, or some other unknown process. But over time, a pattern emerged. Certain sources produced multiple bursts, not just one. They were repeating, sometimes with years between flares, sometimes with much shorter intervals. These became known as soft gamma repeaters, and they hinted at a mechanism entirely different from ordinary pulsars. In parallel, astronomers discovered anomalous X-ray pulsars, neutron stars that shone far brighter in X-rays than their spin rates could explain. The energy they emitted exceeded the power available from their rotation. For years, the nature of these pulsars was debated. Were they accreting material from hidden companions? Or did they represent an entirely new class of object? The eventual realization was that both anomalous X-ray pulsars and soft gamma repeaters were in fact manifestations of the same phenomenon. They were magnetars, powered not by rotation or accretion, but by the decay of immense magnetic fields. The role of space observatories in these discoveries was crucial. Satellites such as the Rossi X-ray Timing Explorer, launched in 1995, provided precise timing of X-ray emissions from neutron stars. SWIFT, launched in 2004, allowed astronomers to respond quickly to bursts and pinpoint their locations. Fermi, launched in 2008, expanded the sensitivity to gamma rays across the sky. Each mission added pieces to the puzzle, showing that the bursts were not random, but the signatures of a small population of extraordinary stars. The repetition, the spectral characteristics, and the sudden flares all pointed toward a new category of astrophysical object. The recognition of magnetars was gradual, built on decades of observations. By the late 1990s, theoretical models had caught up with the data, and the term magnetar was firmly established. Scientists realized that only magnetic fields of 10 to the power of 14 to 10 to the power of 15 Gauss could explain the observed bursts. These fields stored colossal amounts of energy, enough to power outbursts lasting only fractions of a second yet visible across the galaxy. What had begun as unexplained anomalies in satellite data had become one of the most exciting discoveries in modern astrophysics. The story of discovery through gamma and X-ray bursts is therefore a story of surprise. The universe revealed magnetars, not gently, but violently, in flashes that could not be ignored. The same detectors built to guard against human warfare became tools for cosmic revelation, capturing signals from stars whose power dwarfed anything on Earth. It was as though the galaxy itself had shouted across the void, demanding that we pay attention. The bursts that revealed magnetars were unlike any other signals astronomers had encountered. Ordinary pulsars emitted predictable beams of radio waves, spinning with the precision of cosmic clocks. X-ray binaries produced steady streams of energy as matter from a companion star fell onto a neutron star. But the bursts from soft gamma repeaters were different. They came suddenly, often without warning, and they released energy far too great to be explained by rotation or accretion. These eruptions lasted fractions of a second to several minutes, with afterglows that slowly faded. The power involved was staggering, forcing astronomers to confront the reality that a new mechanism must be at work. Throughout the 1980s and 1990s, data accumulated. Each new flare was another piece of evidence. The sources repeated, but not in a way that matched any known pattern. Some bursts came in clusters, others appeared after long silences. The puzzle grew deeper. At the same time, anomalous X-ray pulsars were being catalogued. They rotated more slowly than ordinary pulsars, often with periods of several seconds, yet they glowed persistently in X-rays. Their rotational energy was far too small to explain their brightness. For years, competing theories attempted to explain these objects. Some proposed that they were surrounded by debris disks, feeding them energy. Others suggested hidden binary companions transferring matter, but no evidence for such companions was found. The breakthrough came when theorists connected the dots between the soft gamma repeaters and the anomalous X-ray pulsars. Both classes showed similar spin periods. Both produced bursts of high-energy radiation, and both lacked signs of companions. The only model that fit the evidence was that their energy came from magnetic fields of unprecedented strength. The magnetic decay model explained their persistent emission, their bursts, and their unpredictable behavior. By the late 1990s, the magnetar model was widely accepted, transforming these once mysterious anomalies into a new class of neutron star. The observational record is filled with dramatic examples. The March 5th event of 1979 remained the brightest giant flare for decades, but later, flares challenged even that. In August 1998, SGR 1900+14 erupted with a burst so strong that it saturated detectors. The flare released an initial spike of energy followed by a tail of pulsations, revealing the rotation period of the underlying neutron star. This was one of the clearest demonstrations that magnetars were indeed neutron stars, rotating and emitting pulses of energy in the aftermath of their explosions. The December 2004 flare from SGR 1806-20 became the most powerful ever recorded. The event began with a spike of gamma rays that briefly made the magnetar the brightest object in the sky aside from the Sun, despite lying nearly 50,000 light-years away. The initial spike was followed by a pulsating tail lasting hundreds of seconds, modulated by the star's rotation. The energy released was so immense that it altered Earth's ionosphere, briefly changing the way radio waves propagated through the atmosphere. The sheer scale of this flare made it a defining moment in the study of magnetars. In each of these cases, satellites orbiting Earth became the frontline observers. Swift, Rossi X-ray, Timing Explorer, Fermi, Chandra, and XMM Newton all contributed to building the case. Each mission added new dimensions: precise timing, spectral resolution, rapid follow-up. Together, they transformed bursts that once seemed chaotic into data-rich events that could be dissected and analyzed. The discovery of magnetars was not a single moment, but a series of revelations, each burst opening another door into understanding. What emerged was a picture of neutron stars powered not by rotation, as in pulsars, nor by accretion, as in X-ray binaries, but by magnetic decay. The violent bursts, the persistent X-rays, the spin periods of a few seconds, all fit this model. The anomalies were no longer anomalies, but signatures of the most magnetic stars in the universe. The term magnetar, first coined in the early 1990s, now had a clear observational foundation. These discoveries also reshaped how astronomers thought about neutron stars as a whole. The family of remnants expanded beyond pulsars and binaries to include magnetars as a distinct branch. The realization that magnetism could dominate the life of a star was profound. It showed that even in the small category of stellar remnants, diversity abounded, driven by the details of collapse and the amplification of fields. The sky, once thought to hold only predictable pulsars, now contained wild and violent stars, whose bursts could rival entire galaxies. The story of magnetar discovery is not only about the bursts themselves, but also about how humanity learned to listen for them. In the early years of X-ray and gamma-ray astronomy, instruments were limited and often built with goals far removed from astrophysics. Detectors aboard satellites like Vela were designed to enforce nuclear test ban treaties, not to probe the universe. Yet by chance, they became the first witnesses to explosions taking place across tens of thousands of light years. This is one of the recurring lessons of science, that tools built for practical or political reasons often reveal wonders no one expected. As technology improved, the ability to capture and study these bursts expanded dramatically. Rossi X-ray Timing Explorer, launched in 1995, could measure timing signals with extraordinary precision. It showed how magnetar flares often carried pulsations, matching the spin of the star, proving that these were rotating neutron stars, rather than some unknown new object. SWIFT, launched in 2004, provided rapid follow-up, allowing scientists to capture not only the initial flare, but also the fading afterglow. Fermi, launched in 2008, opened the window to gamma rays across the whole sky, recording bursts from magnetars, as well as other high-energy phenomena. These missions collectively transformed magnetar research from scattered anomalies into a coherent field of study. Case studies reinforce this progress. The flare from SGR 1900+14 in 1998 demonstrated the enormous power of these stars. The flare's pulsating tail, repeating every 5 seconds, revealed the rotation period of the star and linked the emission to a neutron star's spin. The December 2004 giant flare from SGR 1806-20 became a defining benchmark, not only because of its intensity, but because of its reach. Instruments as far away as the Mars Odyssey spacecraft recorded its signal, proving that a magnetar flare can be detected across the solar system. For a brief moment, a single star dwarfed the background of the entire Milky Way in gamma rays. These events also had measurable effects on Earth itself. The December 2004 flare compressed Earth's ionosphere, disrupting how radio waves bounced across the planet. Though the disruption was brief and caused no harm, it was a reminder that cosmic events can reach across light years to influence our world. If such a flare had occurred within a few light years, the effects on satellites, communications, and even the biosphere could have been severe. That this star was nearly 50,000 light-years away and still had measurable impact underscores the unimaginable scale of its power. The classification of anomalous X-ray pulsars and soft gamma repeaters as magnetars unified previously puzzling phenomena. What once seemed like two unrelated groups of stars became a single class, understood through the lens of magnetic energy. Their persistent X-ray glow, their erratic bursts, and their rare giant flares all fit within the framework of magnetic field decay. Theorists had predicted such stars, but it took decades of observational data to confirm their existence. The marriage of theory and observation is what ultimately defined magnetars as a new class of stellar remnant. By the early 2000s, the scientific community accepted magnetars not as exotic speculation, but as established astrophysical reality. As of 2025, about 30 have been confirmed, with many more candidates awaiting confirmation. Each detection adds to the population, though their rarity ensures they remain special. Unlike pulsars, which number in the thousands, magnetars are uncommon jewels scattered across the galaxy. But when one of them erupts, it can be brighter than all the pulsars combined. The discovery of magnetars through gamma and X-ray bursts has reshaped our view of the violent universe. It has shown us that neutron stars are not monolithic but diverse, their properties sculpted by mass, spin, and magnetic field. It has also shown us that the most powerful signals often arrive without warning, demanding attention from instruments that are always watching the sky. Each flare is both a challenge and an invitation, a cosmic announcement that the most magnetic stars have spoken again. And so Chapter 4 closes with the realization that magnetars revealed themselves not gradually, but in flashes of overwhelming power. They forced their way into our awareness through signals that no scientist could ignore, bursts that traveled across space to strike our detectors and even affect our planet. The next step is to ask not just how we discovered them, but what these discoveries mean for physics itself. How do magnetic fields, so extreme, shape the behavior of matter and light? In the following chapter, we will descend into the physics of extreme magnetism, exploring how magnetars turn invisible forces into the most violent displays the universe can produce. To understand magnetars fully, one must enter a domain where the familiar rules of physics begin to stretch and sometimes to fracture. On Earth, magnetism is a subtle force. It aligns compasses, powers, motors, and shields our planet from solar wind. Even in neutron stars, with ordinary fields of 1 trillion Gauss, magnetism is immense, but still secondary to gravity and rotation. In magnetars, however, the magnetic field is not a minor influence, but the central driver of everything the star does. At 10 to the power of 15 Gauss, magnetism becomes a dominant form of energy, shaping matter, light, and even the structure of space itself. To grasp such a field, consider that a refrigerator magnet is a few hundred Gauss. Earth's field is about half a Gauss. The strongest steady fields ever created in laboratories are tens of millions of Gauss, far short of what magnetars generate naturally. At 1 trillion Gauss, atoms themselves distort, electron orbits compressing along field lines. At 10 to the power of 15 Gauss, the physics of atoms gives way to the physics of quantum electrodynamics. Light, which normally travels through vacuum unhindered, now interacts with the magnetic field. Vacuum birefringence occurs, meaning empty space acts like a crystal, splitting photons into different polarizations. This phenomenon, predicted decades ago, has been confirmed indirectly in observations of neutron stars and is thought to occur most strongly in magnetars. The energy stored in a magnetar's field is colossal. Estimates suggest that the magnetic field of a single magnetar contains more total energy than all the nuclear reactions that will occur in our Sun over its 10 billion year lifetime. This energy does not remain quiet. As the star's interior evolves, magnetic stresses twist and tangle. The crust, though stronger than any material on Earth, eventually cracks under the strain. These fractures produce starquakes, seismic events that ripple through the 20-kilometer sphere. The sudden rearrangement of magnetic field lines accelerates particles, releases radiation, and produces bursts of gamma rays visible across the galaxy. The connection between magnetic stress and flares is now well established. When field lines reconnect, energy is liberated in a manner similar to solar flares on our own star. but magnified to unimaginable scales. A solar flare might release energy equivalent to billions of hydrogen bombs, but a magnetar flare can exceed that by factors of millions. The giant flare of December 2004 from SGR 1806-20 released in a fraction of a second as much energy as the Sun radiates in 100,000 years. This event, recorded across the solar system, remains one of the most extreme outbursts of energy ever witnessed. Beyond radiation, extreme magnetism affects the very stability of the star. The crust may oscillate during and after flares, producing quasi-periodic oscillations in the emitted X-rays. These oscillations allow astronomers to probe the internal structure of magnetars, much like seismologists probe Earth by studying earthquakes. Each oscillation carries information about the density and elasticity of matter under extreme pressure. In this way, magnetars become laboratories for nuclear physics, offering data about matter compressed to densities far beyond those achievable in any terrestrial experiment. The study of extreme magnetism also illuminates the limits of quantum electrodynamics. In ordinary conditions, QED effects are subtle, requiring precision experiments with lasers and accelerators. In a magnetar, they are written into the very behavior of light and matter. Photon splitting, in which a high-energy photon spontaneously divides into two lower-energy photons, becomes possible in fields above 10 to the power of 13 Gauss. This process alters the spectrum of radiation leaving the magnetar, leaving fingerprints that can be detected by telescopes. Vacuum birefringence alters polarization, another signature, awaiting precise measurement. These are not theoretical curiosities, but real consequences of fields so strong they make empty space behave like a material substance. In these ways, magnetars force us to confront physics at its most extreme. They demonstrate that magnetic fields are not merely forces we manipulate in laboratories, but fundamental actors in the cosmos. They twist light, fracture stars, and radiate energy on scales that dwarf entire solar systems. By studying them, we glimpse not only the nature of neutron stars, but the deeper laws of physics itself. The magnetic field of a magnetar is not only vast in strength, but also dynamic, evolving over thousands of years, in ways that both reveal and conceal its power. Inside the star, magnetic fields are wound like taut springs, coiled by the motion of charged particles during the violent birth of the neutron star. As time passes, these fields begin to unwind and decay. The energy released in this slow decay is converted into heat, keeping the surface of the magnetar warmer than ordinary neutron stars of the same age. It is why magnetars shine persistently in X-rays. Even without bursts, their very existence as glowing, restless objects is proof of the power of decaying magnetism. The physics of crustal failure is central to this picture. The outer shell of a magnetar is only about 1 kilometer thick, but it is the strongest solid known in the universe. The crystalline lattice of neutron star crust is billions of times stronger than steel. Yet even this strength is no match for the stresses imposed by a magnetic field of 10 to the power of 15 Gauss. As the internal field twists, the crust strains like the surface of a world under tectonic pressure. Eventually, the tension exceeds the breaking point. The crust cracks, seismic waves ripple through the star, and magnetic energy is released explosively into space. The result is a burst of gamma rays that can outshine entire galaxies for a fraction of a second. These starquakes are often compared to earthquakes on Earth, but the scales involved are vastly different. An earthquake might release the energy equivalent of 1 million tons of TNT. A magnetar flare can exceed this by factors of 1 billion. The comparison highlights how inadequate human experience is for grasping the magnitude of these events. They are catastrophes on a cosmic scale, the breaking of a stellar crust beneath the strain of a magnetic force that defies comprehension. The connection between magnetic fields and radiation also explains the unique spectra of magnetar flares. Unlike pulsars, which radiate primarily in radio waves, magnetars erupt in high-energy photons, Gamma rays and X-rays dominate their emissions because the magnetic field accelerates particles to near the speed of light, forcing them to radiate at extreme energies. In some models, pairs of electrons and positrons are ripped from the vacuum, creating a storm of matter and antimatter in the magnetosphere. These pairs then annihilate, producing bursts of radiation that contribute to the flare. Each observation helps refine these models, showing how extreme magnetism translates into extreme light. The magnetosphere of a magnetar is itself an exotic environment. On Earth, the magnetosphere shields us from solar wind and guides charged particles into auroras. Around a magnetar, the magnetosphere is a prison of unimaginable strength. Charged particles are trapped in magnetic loops that can stretch thousands of kilometers into space. When these loops twist and snap, they release energy in a process similar to solar coronal mass ejections, but magnified by factors of trillions. The complexity of this region challenges even advanced simulations, but it is here that much of the visible drama of magnetars unfolds. What makes magnetars even more remarkable is that their magnetic energy not only shapes their own behavior but also affects their surroundings. A giant flare sends a flood of radiation racing outward, ionizing gas and altering the interstellar medium. If such an event occurred within a few dozen light-years of Earth, the effects could be profound, stripping away portions of the atmosphere or disrupting the biosphere. Thankfully, the known magnetars are far enough away to pose no direct danger, yet the very fact that they can influence distant space reminds us of their place as cosmic hazards as well as cosmic laboratories. Observations of magnetar bursts also provide tests of relativity and nuclear physics. The oscillations detected in the tails of giant flares are thought to be vibrations of the star itself, allowing scientists to probe its interior. These quasi-periodic oscillations act like fingerprints, encoding the properties of matter under conditions billions of times denser than atomic nuclei. By comparing these oscillations to theoretical models, researchers hope to learn whether exotic forms of matter exist at the core of neutron stars. Magnetars thus serve as seismic experiments written into the fabric of the universe, allowing us to explore physics beyond the reach of any machine built on Earth. At the heart of these studies is a deeper truth. Magnetars remind us that the laws of physics are not abstract equations confined to laboratories, but forces that sculpt entire stars. Gravity, quantum mechanics, and magnetism all meet in their compact spheres, producing consequences that radiate across the cosmos. When we observe a magnetar flare, we are not only watching a star quake under magnetic stress, we are also watching the universe demonstrate its own fundamental laws at their limits. The physics of magnetars is ultimately the physics of extremes, and nowhere is this more evident than in the comparison between their magnetic fields and every other magnetic environment known to us. On Earth, magnetic fields influence compasses and protect our planet from solar radiation, yet they are weak enough that we rarely think of them as forces of destruction. Even in ordinary neutron stars, the field is powerful, but still secondary to the crushing weight of gravity. In magnetars, however, the field contains more energy than gravity itself can comfortably confine. The star is held together in part by quantum mechanical pressure, but its surface and interior are constantly strained by the restless, shifting energy of the magnetic field. This tension explains why magnetars are so unstable compared to ordinary pulsars. A pulsar can rotate for millions of years, gradually spinning down in a predictable way, its energy output fading steadily over time. A magnetar, by contrast, lives in a state of constant pressure and occasional violent release. The crust bends and cracks, the magnetic field shifts, and radiation is emitted in sudden bursts. This is why magnetars are most often detected through outbursts rather than steady signals. Their physics is not calm and gradual, but restless and explosive. The December 2004 flare from SGR 1806-20 remains the most striking example. At the moment of the initial spike, the luminosity reached levels higher than all other X-ray sources in the sky combined. The burst lasted only a fraction of a second, but its afterglow persisted for hundreds of seconds, modulated by the rotation of the star. Observers on Earth saw the ionosphere ripple under the impact of the radiation. Spacecraft across the solar system recorded the flare, a reminder that magnetars are capable of events that cannot be ignored, even from vast distances. That such an explosion came from a star no larger than a city illustrates the compression of energy and force that defines their existence. In theoretical terms, the study of magnetars forces us to revisit the interplay between gravity, nuclear physics, and electromagnetism. The core of a neutron star may contain exotic states of matter, from superfluids of neutrons to condensates of quarks. The magnetic fields threading this matter interact in ways we only partly understand. Models suggest that magnetic decay proceeds through ambipolar diffusion and Hall drift, processes in which currents inside the star gradually rearrange. These terms may sound abstract, but they describe how energy is redistributed over thousands of years, shaping the lifespan of the magnetar. Each observed flare provides data that constrains these models, helping physicists refine their understanding of how magnetic energy is stored and released. Magnetars also highlight the intimate link between microphysics and macrophysics. On one hand, the Pauli exclusion principle, a rule of quantum mechanics that applies to subatomic particles, allows neutron stars to exist at all. On the other hand, the enormous structures of galaxies are influenced by the collective energy released by stars like magnetars. A principle governing the behavior of individual neutrons underpins objects that can shape the dynamics of entire galaxies. This is the scale of physics that magnetars bring into focus. As extreme as they are, magnetars are also fleeting in cosmic terms. Their magnetic fields decay over tens of thousands of years, a short span compared to the billions of years that stars and galaxies endure. Once their fields weaken, they fade into quieter neutron stars, indistinguishable from their less magnetic cousins. This means that the magnetars we observe now are young, their energy still fresh from the violence of their birth. In the deep future, they will be silent, their fields gone, their crusts cooled, their brilliance extinguished. But for now, they live as firebrands of astrophysics, short-lived, yet spectacular. For scientists, this fleeting nature makes every observation precious. Because magnetars are rare and short-lived, each burst of radiation is an opportunity that may not repeat. Telescopes across the world and in orbit stand ready to capture their signals, knowing that seconds can make the difference between missing and understanding a cosmic event. The collaboration between instruments, from radio arrays to spaceborne gamma-ray detectors, reflects how valuable these opportunities are. Each flare, no matter how brief, can carry answers to questions about quantum electrodynamics, nuclear matter, and the stability of stars. The study of extreme magnetism in magnetars is therefore not only about cataloging rare stars, but about probing the very boundaries of physics. They show us matter under densities billions of times greater than lead, fields trillions of times stronger than laboratory magnets, and energies that dwarf our sunday. They remind us that the laws of nature are not fixed to familiar scales, but extend into realms that challenge human imagination. To explore magnetars is to explore the outer limits of what is possible in the universe. And so, Chapter 5 closes with the recognition that magnetars are more than astronomical curiosities. They are demonstrations of the power of magnetic fields when magnified to cosmic proportions. They fracture their own crusts, release bursts that can be seen across half the galaxy, and turn quantum effects into macroscopic realities. They are, in every sense, the physics of extreme magnetism made visible. In the next chapter, we will consider not only what happens within the stars themselves, but also what happens beyond them. We will ask how magnetars influence the space around them, and what risks and consequences their outbursts might carry for the galaxy, and even for Earth itself. Every burst from a magnetar is not contained within the star itself. The energy released races outward at the speed of light, flooding the surrounding space with radiation. While the star may be only a few dozen kilometers wide, its influence can extend across light years. The magnetosphere, twisted by immense magnetic fields, flings charged particles into space, and giant flares unleash storms of gamma rays that sweep through the galaxy. The question then arises, what impact do these violent events have on their cosmic neighborhoods? And what would happen if one occurred close enough to Earth? The interstellar medium, the thin gas and dust between stars, is shaped by many forces, from the steady winds of ordinary stars to the explosions of supernovae. A magnetar flare is another actor in this cosmic drama. When a burst erupts, it ionizes the gas it encounters, heating and accelerating particles. Over thousands of years, repeated outbursts can carve cavities, altering the balance of pressure and chemistry in the surrounding region. Observations of supernova remnants hosting magnetars suggest that their bursts inject additional energy, changing the dynamics of the expanding clouds. In this sense, magnetars participate in the recycling of matter in galaxies, not only through the explosions that created them, but through the flares that continue to shape their environment. For Earth, the most vivid reminder of this potential came in December 2004. The giant flare from SGR 1806-20 was nearly 50,000 light-years away, yet its radiation was strong enough to compress our planet's ionosphere. Instruments recorded sudden disturbances as high-energy photons poured into the upper atmosphere. The flare was brief and caused no harm, but it demonstrated that magnetar outbursts are not only visible but tangible, their effects measurable even across half a galaxy. Had such a flare occurred within a few dozen light-years, the consequences could have been serious. Satellites could have been damaged, communication systems disrupted, and in the most extreme cases, biological systems affected by ionizing radiation. The possibility of a nearby magnetar flare raises natural questions about the risks to life on Earth. Astrophysicists have examined this scenario carefully. The consensus is that while a giant flare within a few light-years could indeed damage the ozone layer or disrupt ecosystems, the probability of such an event is vanishingly small. Magnetars are rare, and none are known within such dangerous proximity. The closest confirmed magnetars lie thousands of light-years away, far enough to pose no threat. Still, the study of these risks highlights how even distant stars can remind us of our vulnerability in the wider cosmos. Magnetars also influence the space around them in subtler ways. Their persistent X-ray emission and smaller bursts steadily bathe their surroundings in radiation. For any nearby planets or potential stellar companions, this radiation could be destructive, stripping atmospheres or sterilizing surfaces. In regions where star formation is active, magnetar flares may alter the chemistry of interstellar clouds, affecting the conditions under which new stars and planets form. The impact of magnetars is therefore both immediate, in sudden bursts, and long-term, in continuous radiation. They are engines of change in the delicate ecosystems of galaxies. The study of these effects has practical importance. By understanding how magnetars influence their environments, scientists gain insight into the limits of habitability in the universe. Planets too close to a magnetar would face constant radiation, making life as we know it impossible. This consideration helps refine the search for habitable worlds by reminding us that the neighborhood of a star matters as much as the star itself. It also deepens our appreciation of the stability of our own sun, whose calmness allows life to flourish on Earth. The impact of magnetars, then, is not limited to their internal physics, but extends outward, shaping the interstellar medium, affecting distant planets, and occasionally reaching all the way to Earth. They are reminders that the universe is connected, that events across light years can still touch us, and that the violent skies we observe are not entirely separate from the world we inhabit. The consequences of magnetar flares extend into the very fabric of interstellar space. Radiation from these outbursts ionizes gas clouds, stripping electrons from atoms and changing the chemistry of the medium. Over long timescales, Repeated flares can deposit enough energy to alter how matter clumps together to form new stars. Supernova explosions already enrich and disturb the interstellar medium, but the afterlife of a massive star, as a magnetar, adds another layer of turbulence. This means that the cycle of stellar birth and death is not just punctuated by explosions, but also by continuing injections of energy from the remnants themselves. On a local scale, magnetars can sculpt the regions around them through continuous emission. Their strong magnetic fields trap charged particles, creating a harsh environment similar in principle to Earth's radiation belts, but magnified to extremes. Any nearby planets or stellar companions would be bombarded by radiation levels high enough to sterilize surfaces and strip atmospheres. This suggests that while magnetars are fascinating to study, they are among the least hospitable stars in the galaxy. Their presence sets a limit on where life could reasonably develop. Worlds in their neighborhoods would face storms of particles and bursts of gamma rays with no chance of survival. From Earth's perspective, the 2004 flare from SGR 1806-20 was a turning point. Satellites across the solar system, including spacecraft orbiting Mars, recorded the outburst. For a brief instant, it was brighter than any other source in the gamma-ray sky. Its influence on Earth's ionosphere was measurable, changing how radio waves traveled through the upper atmosphere. Though the effect faded quickly, it showed that magnetars could make themselves felt across the cosmos. If a flare of similar magnitude had occurred within a few tens of light years, it could have been catastrophic. Scientists have estimated the potential consequences of such an event. A giant flare closer than about 10 light years could strip away portions of Earth's ozone layer, exposing the surface to harmful ultraviolet radiation. From the Sunday, ecosystems would be stressed, and mass extinctions could result. Fortunately, no known magnetars lie anywhere near this distance. The nearest confirmed examples are thousands of light years away, well outside the danger zone. Still, the possibility underscores a broader truth. Life on Earth depends not only on the stability of our sun, but also on the relative calm of our galactic neighborhood. The rarity of magnetars and the vast distances between stars make the likelihood of such a nearby flare extraordinarily low. Extinction-level events from magnetars are therefore considered unlikely by astrophysicists. Yet the very fact that such risks exist reminds us that the cosmos is not a safe or predictable place. Planets orbiting other stars may not be as fortunate. A world located only a few light years from a magnetar would face a harsh bombardment of radiation that could prevent life from ever arising. The presence of magnetars in star-forming regions may thus influence which planetary systems remain viable for habitability. Beyond the question of risk, magnetars are useful in another way. Their bursts provide natural laboratories for studying how radiation interacts with planetary atmospheres. By measuring how Earth's ionosphere responded to the 2004 flare, scientists learned how high-energy photons change atmospheric chemistry. This knowledge can be applied to understanding exoplanetary systems, where bursts of radiation from host stars or nearby remnants could dramatically alter the conditions for life. In this way, even a cosmic hazard becomes a scientific tool, teaching us more about the fragile balance that allows planets to sustain life. In the end, the impact of magnetars on space environments is a story of both danger and discovery. Their outbursts remind us of the destructive potential of the universe, but they also illuminate how stars shape galaxies, how radiation shapes atmospheres, and how the delicate thread of habitability is maintained. Each flare carries not only energy but also information, showing us how the cosmos works on scales far beyond Earth. The influence of magnetars also reaches into the field of planetary protection, a discipline concerned with the long-term safety of life-bearing worlds. While our own solar system is fortunate to be distant from any magnetar, the possibility that other planetary systems might not share this luck raises important questions. If a giant flare could sterilize or strip a nearby planet, then the distribution of magnetars across the galaxy might play a role in determining where habitable worlds can exist. This perspective links the rare outbursts of magnetars to the larger question of life in the universe. The violent skies do not only shape matter and stars, they also shape the conditions under which life can arise or be extinguished. One of the striking lessons of the December 2004 flare is how fragile Earth's environment can be when exposed to cosmic radiation. The flare was 50,000 light-years away, yet still caused measurable changes in the ionosphere. Radio communication was briefly disrupted, and satellites recorded surges in energy levels. These effects were mild compared to what a closer flare could do, but they were enough to remind scientists that our planet's shield is not absolute. The atmosphere can absorb and deflect enormous amounts of energy, yet in the face of cosmic extremes, it shows its limits. Theoretical studies of atmospheric chemistry suggest that a giant flare within about 10 light-years could cause ozone depletion significant enough to allow dangerous levels of ultraviolet radiation to reach the surface. This would not necessarily destroy all life, but it could devastate ecosystems and trigger mass extinctions. Some researchers have even speculated that past extinction events on Earth might have been influenced by cosmic radiation, though there is no direct evidence linking any extinction to a magnetar. Such ideas remain cautious hypotheses rather than proven facts. Still, the possibility is a reminder that the history of life on Earth is entwined with the history of the cosmos. Beyond planetary atmospheres, magnetar flares also influence the broader structure of galaxies. Their bursts inject energy into the interstellar medium, heating and stirring gas clouds that later collapse to form new stars. In this way, magnetars participate in the endless recycling of matter that builds galaxies. Just as supernovae enrich the cosmos with heavy elements, magnetars seed the galaxy with bursts of energy that help regulate star formation. The Milky Way we see today is not only shaped by calm processes of gravity, but also by violent injections of energy from its most extreme stars. For astronomers, the role of magnetars as cosmic hazards is balanced by their role as cosmic beacons. Because their bursts can be detected across vast distances, they serve as markers of extreme environments. Each flare is a signal that can be studied to understand the properties of interstellar space, the response of planetary atmospheres, and the behavior of matter under intense stress. Even as they remind us of potential risks, they also provide unique opportunities for scientific discovery. Their violence becomes our source of knowledge. Ultimately, the impact of magnetars on space environments is a paradox. They are destructive, yet they contribute to the cycles that make life possible by shaping the interstellar medium. They are dangerous, yet they are too distant to pose real threats to Earth. They are rare, yet their bursts dominate the high-energy sky when they occur. This duality captures much of the nature of the universe itself, where forces that create also destroy, and where destruction often leads to new creation. As Chapter 6 draws to a close, the message is clear. Magnetars are not isolated curiosities, locked within their neutron star shells. They are actors in a wider story, influencing planets, altering atmospheres, stirring gas clouds, and even brushing against Earth itself across light-years of space. Though the chances of a nearby giant flare affecting our world are remote, the very possibility places magnetars among the short list of cosmic hazards that remind us of our place in a volatile universe. In the next chapter, we will shift from hazards to mysteries, turning to one of the most puzzling signals in modern astronomy. We will ask how magnetars may be connected to the enigmatic flashes of radio waves known as fast radio bursts, and whether these magnetic stars hold the key to unlocking another great cosmic riddle. In the early years of the 21st century, astronomy encountered a new and baffling signal. In 2007, while analysing archival data from the Parkes Radio Telescope in Australia, astronomers discovered a millisecond-long flash of radio waves unlike anything seen before. The burst was extraordinarily bright, arriving from billions of light-years away, yet it lasted less than the blink of an eye. Its dispersion pattern, the way different radio frequencies were delayed as they passed through interstellar plasma, proved that it had traveled a vast distance through space. The mystery was immediate and profound. What could produce such an intense burst of radio waves, lasting only a fraction of a second, but visible across the universe? This was the birth of the field of fast radio bursts, or FRBs. At first, many scientists wondered if these signals might be artifacts, perhaps caused by terrestrial interference or glitches in instruments. But as more examples were found, the reality became clear. The bursts were genuine astrophysical phenomena, arriving from distant galaxies. Each carried energy equivalent to the total output of the Sun over days or even weeks, compressed into milliseconds. The sheer intensity of FRBs made them one of the most puzzling discoveries in modern astronomy. From the beginning, magnetars were considered possible culprits. Their powerful magnetic fields, their ability to produce sudden bursts of energy, and their known activity at high energies all made them plausible candidates. The challenge was evidence. FRBs were first detected from billions of light-years away, and their exact sources were difficult to pinpoint. Without clear localization, astronomers could only speculate. Other models were proposed, from collisions of neutron stars to exotic phenomena involving black holes. But magnetars remained among the most compelling possibilities, since they were already known to produce violent bursts of radiation across the spectrum. For more than a decade, the debate continued. Each new detection added fuel to the mystery. Some FRBs repeated, flashing again and again from the same location. Others were one-off events, never seen again. The repeating bursts suggested that the sources were not catastrophic events like mergers, which destroy their progenitors. Instead, they must come from objects that could flare repeatedly without self-destruction. This fit well with the magnetar model, since magnetars are known for producing multiple bursts over their short lifetimes. The breakthrough came in April 2020, when the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, detected a fast radio burst from within our own galaxy. Unlike earlier FRBs, which came from billions of light-years away, this one was close enough to identify its origin. Almost simultaneously, X-ray satellites recorded bursts from a known magnetar, SGR 1935+2154. The coincidence was too strong to ignore. For the first time, an FRB had been directly linked to a magnetar. The event demonstrated that at least some fast radio bursts are indeed produced by these magnetic neutron stars. The implications were enormous. Magnetars could finally be tied to one of the great mysteries of modern astronomy. The detection confirmed that the mechanisms within magnetar magnetospheres, or the cracking of their crusts, could generate bursts of radio waves powerful enough to be seen across galaxies. It also explained the repeating nature of some FRBs. Just as magnetars can produce multiple gamma-ray flares over their lifetimes, they can also produce multiple radio bursts. Not every FRB may come from magnetars, but the connection is undeniable. With this discovery, the study of magnetars gained a new dimension. They were no longer only sources of gamma rays and X-rays, but also linked to enigmatic radio signals arriving from the farthest reaches of the cosmos. Their magnetic storms, already known as some of the most violent events in the universe, now seemed capable of producing a new form of cosmic communication, brief and brilliant, flashing across intergalactic space. The link between magnetars and fast radio bursts has transformed both fields. For years, fast radio bursts were seen as exotic puzzles, sometimes even prompting speculation about unknown astrophysical objects or advanced civilizations. The identification of a magnetar in our own galaxy as the source of a fast radio burst showed that no extraordinary explanations were needed. The universe itself provides natural engines powerful enough to generate these signals. A magnetar, with its magnetic field twisted and cracking, can produce flashes of radio waves strong enough to outshine an entire galaxy for a moment. Still, the discovery of one connection did not end the mystery. Fast radio bursts come in many varieties. Some repeat regularly, with bursts separated by hours, days, or months. Others flare only once and are never seen again. Magnetars can explain this diversity. Since their activity is unpredictable, some may enter periods of heightened stress, producing repeated bursts as their crusts fracture again and again. Others may flare only once in a century, releasing their energy in a single catastrophic event. The magnetar model can account for both repeating and one-off FRBs, though other mechanisms may contribute as well. The physics behind how magnetars generate these radio flashes is still debated. One idea is that a starquake alters the magnetic field lines around the star, creating an electromagnetic shock that accelerates particles to near the speed of light. These particles emit coherent radio waves, which travel across space as a fast radio burst. Another idea involves magnetic reconnection in the magnetosphere, similar to solar flares, but vastly more powerful. In either case, the processes occur in milliseconds, explaining the short duration of FRBs. The magnetar's extreme magnetic field provides the reservoir of energy needed to power such sudden events. Observations since 2020 have strengthened the connection. CHIME and other radio telescopes have detected repeating FRBs with properties consistent with magnetar activity. Some bursts appear polarized in ways that suggest they pass through strong magnetic environments, another clue pointing to magnetar origins. Meanwhile, X-ray and gamma-ray satellites continue to monitor known magnetars for correlated bursts. Each new detection narrows the gap between theory and observation, refining our understanding of how magnetars produce these enigmatic signals. What makes FRBs particularly exciting is their usefulness as cosmic tools. Because the bursts are bright and travel great distances, they can be used to probe the matter between galaxies. As radio waves pass through plasma, they are delayed in frequency-dependent ways. By measuring this dispersion, astronomers can estimate how much material lies along the path. FRBs therefore serve as cosmic lighthouses, illuminating the otherwise invisible distribution of baryonic matter in the universe. Magnetars, by producing FRBs, inadvertently provide scientists with probes of intergalactic space. The discovery also deepens our sense of connection between different branches of astrophysics. For decades, magnetars were studied mainly in X-rays and gamma rays, while radio astronomers puzzled over fast bursts of unknown origin. Now these two fields intersect. A single type of object, the magnetar, unites both domains, showing that high energy and radio astronomy are not separate worlds, but parts of the same cosmic story. This synthesis demonstrates the power of multi-wavelength and multi-messenger astronomy, where signals across different forms of radiation combine to tell a fuller story. Despite these breakthroughs, challenges remain. Not every fast radio burst may come from a magnetar. Some occur in environments where no young magnetars are likely to exist. Others are too energetic to be easily explained by known magnetar models. It is possible that multiple sources contribute. Some FRBs from magnetars, others from different phenomena, such as neutron star mergers or black hole interactions. The diversity of signals suggests a diversity of origins, but what is clear is that magnetars are at least one of the main contributors, and perhaps the dominant one, to the population of fast radio bursts observed today. The study of FRBs linked to magnetars is still young. Future instruments, such as the Square Kilometre Array, promise to detect thousands of FRBs, many of them in detail precise enough to locate their host galaxies and environments. These discoveries will test whether magnetars truly dominate the FRB population, or whether other sources play larger roles than we now realize. Either way, magnetars have already secured their place as central actors in this mystery, showing once again that the most magnetic stars in the universe are also some of the most communicative. The realization that magnetars can produce fast radio bursts has not only solved part of a mystery, but also created new questions. One of the most pressing is how such immense energy is funneled into radio waves with such extraordinary efficiency. A single FRB carries as much energy as the sun emits over days or weeks, yet it is confined to milliseconds of time and a narrow slice of the electromagnetic spectrum. This requires a coherent emission process, where countless particles act in unison to amplify the signal. On Earth, coherent radio emission is achieved in transmitters and lasers through careful engineering. In a magnetar, it occurs naturally, guided by fields and forces billions of times stronger than anything humans can control. The discovery of repeating FRBs adds another layer of intrigue. In 2016, astronomers identified FRB 121102, a repeating source located in a dwarf galaxy 3 billion light-years away. It emitted bursts over years, sometimes dozens in a single day. Such persistence suggested that the source could not be a catastrophic event, like a merger. The magnetar hypothesis gained strength, as magnetars are known for episodic flaring over their short lifespans. Later, other repeating FRBs were found, many showing variations in strength, frequency, and polarization. Each one reinforced the idea that magnetars, with their volatile behavior, could account for at least a substantial portion of the population. The April 2020 burst from SGR 1935 plus 2154 in our own galaxy remains the most direct evidence, but it also revealed complexities. The FRB detected was weaker than the extragalactic ones seen billions of light-years away. This raised questions about whether the brightest FRBs observed across the universe require more extreme magnetars or different mechanisms. Perhaps some bursts involve unusually young magnetars, only decades or centuries old, still brimming with magnetic energy. Or perhaps multiple processes can produce FRBs, with magnetars being only one channel among several. The scientific importance of FRBs extends far beyond their origins. Because they are visible across vast distances, they serve as cosmic probes. The dispersion of their radio waves provides measurements of the total amount of ionized gas between galaxies, a key to solving the long-standing problem of the universe's missing baryons. Each FRB is not only a flare from a distant star, but also a tool for mapping the invisible matter that fills the cosmos. In this way, magnetars inadvertently help scientists answer one of the biggest questions in cosmology. For the public imagination, FRBs also represent one of the most dramatic forms of cosmic communication. Bursts of radio waves arriving from across billions of light-years sound almost like messages, brief signals flashing through the void. While early speculation about artificial origins has given way to natural explanations, the drama of FRBs continues to capture attention. That they come, at least in part, from magnetars only deepens their fascination. The most magnetic stars in the universe are also some of its loudest, sending brief but powerful cries across intergalactic space. The connection between magnetars and FRBs shows how science advances through patience, persistence, and the convergence of multiple lines of evidence. For years, FRBs were unsolved puzzles. For decades, magnetars were extreme but isolated curiosities. When the two fields intersected, both were transformed. Magnetars gained a new significance as engines of radio waves, and FRBs gained a natural explanation grounded in known astrophysics. This is the power of astronomy, to take disparate mysteries and show that they are pieces of the same cosmic puzzle. As the chapter closes, one truth stands out. Magnetars are not only dangerous stars, but also messengers. Their bursts of gamma rays and X-rays reveal the violence of their crusts and fields. Their flashes of radio waves reveal the structure of the universe itself, tracing the matter between galaxies. They are both hazards and tools, threats and teachers. The study of magnetars and fast radio bursts is still in its early stages, but already it has reshaped our view of the cosmos. In the chapters ahead, we will leave the realm of discovery and physics to explore how these extreme stars echo in human culture, imagination, and the way we communicate science itself. The study of magnetars today stands on the threshold of extraordinary discovery. What began as unexplained bursts in the 1970s has become a thriving field at the cutting edge of astrophysics. Yet, despite decades of progress, magnetars remain elusive. They are rare, unpredictable, and short-lived on cosmic timescales. Only about 30 confirmed magnetars are known in the Milky Way, and their flares cannot be forecast. They erupt without warning, demanding constant vigilance. For astronomers, this rarity and unpredictability transform each detection into an event of global collaboration, with observatories and satellites across Earth and in orbit racing to capture fleeting signals before they fade. Much of the frontier lies in observation. Instruments such as NASA's Chandra X-ray Observatory and ESA's XMM Newton continue to provide high-resolution spectra of magnetar outbursts, showing how their emission evolves over seconds and minutes. Swift and Fermi remain on guard for sudden gamma-ray flashes, while NICER, mounted on the International Space Station, times pulsations with exquisite precision. Together, these observatories form a distributed network, always listening for the next eruption. They allow astronomers to probe details of magnetar behavior that were once unimaginable, such as the quasi-periodic oscillations in the tails of giant flares. These oscillations act like the ringing of a bell, carrying clues about the internal structure of the star. In this way, bursts become tools, letting us study matter at densities greater than any terrestrial experiment could reach. The next generation of observatories promises even more. Athena, the European Space Agency's planned X-ray telescope, will provide unprecedented sensitivity, capable of detecting fainter and more distant magnetars. The proposed Lynx mission could go further still, imaging emissions with unmatched clarity. On the ground, radio arrays like CHIME in Canada and the future Square Kilometre Array will detect thousands of fast radio bursts, many of which are expected to originate from magnetars. These instruments will not only increase the number of known magnetars, but also reveal their diversity, tracing how they behave in different environments across galaxies. Another frontier is multi-messenger astronomy. The detection of gravitational waves from merging neutron stars in 2017 demonstrated that the universe speaks in more than light. Magnetars, with their starquakes and violent flares, may also emit gravitational waves. If detectors such as LIGO, Virgo, or future observatories like Cosmic Explorer were to capture such a signal, it would provide a direct probe of a magnetar's interior, revealing how matter behaves under pressures billions of times higher than in atomic nuclei. Similarly, neutrino detectors like IceCube may one day register bursts of these ghostly particles during magnetar outbursts, adding yet another voice to the chorus. The promise of multi-messenger detections keeps researchers watching, waiting for the day when a flare is accompanied not only by photons, but by space-time ripples or streams of neutrinos. The theoretical frontier is equally alive. Supercomputer simulations are now able to model the collapse of massive stars and the birth of magnetars in remarkable detail. These models track how rotation and convection amplify magnetic fields to the astonishing levels observed. They attempt to explain why some neutron stars become magnetars, while others emerge as ordinary pulsars. Is it a matter of initial spin rate, mass, or turbulence during collapse? Or are there deeper differences in stellar evolution, perhaps shaped by binary interactions or metallicity? Simulations also probe how magnetic fields decay over tens of thousands of years, unraveling processes such as ambipolar diffusion and Hall drift. Though these terms are abstract, they describe real physical processes by which magnetic stresses evolve inside the densest matter in the universe. Magnetars are also being linked to some of the brightest explosions known, superluminous supernovae, far more radiant than ordinary stellar deaths, may be powered by newborn magnetars that spin hundreds of times per second, injecting rotational energy into their expanding shells. Similarly, some long-duration gamma-ray bursts, cosmic flashes, visible across billions of light years, may be driven not by black holes, as once thought, but by hyper-energetic magnetars at the moment of their birth. If true, then magnetars are not just curiosities, but central players in the most luminous phenomena of the universe, hidden engines behind cosmic fireworks. The connection to fast radio bursts is another frontier transforming the field. Since the detection in 2020 of an FRB from a galactic magnetar, astronomers have pursued the idea that many FRBs across the universe originate from magnetars. Each burst, lasting only milliseconds, carries energy equivalent to days or weeks of solar output. Radio telescopes now catch hundreds of these signals, some repeating with surprising regularity. Linking them to magnetars not only solves a mystery, but provides a tool for cosmology. FRBs act as probes of intergalactic matter, mapping the otherwise invisible plasma that fills the spaces between galaxies. Magnetars in this way become instruments of measurement, unwittingly helping scientists chart the universe. Yet at every step, questions remain. Why do magnetars flare when they do? What precise physical processes turn magnetic stress into light and radio waves? How many magnetars exist in galaxies beyond our own? Do they evolve into ordinary pulsars once their fields decay? Or do they fade into silence, indistinguishable from other neutron stars? Each mystery fuels new observations, new models, and new experiments. The frontiers of magnetar research thus lie not in a single discovery, but in a constellation of questions, each demanding new tools and new perspectives. They show us the interplay of observation and theory, of collaboration and patience. They remind us that even in a universe we have studied for centuries, true mysteries remain. Magnetars are not solved puzzles but ongoing challenges, laboratories of the extreme waiting to be unlocked. As this chapter closes, we stand at the edge of knowledge. Magnetars are now recognized as the most magnetic stars in the cosmos, engines of bursts and flares, possible sources of fast radio bursts, and perhaps the powerhouses behind some of the brightest explosions known. Yet they remain mysterious, unpredictable, and incomplete in our understanding. The next decades promise breakthroughs, but the mystery will always endure. For magnetars embody the universe at its most creative and violent. And it is in these extremes that we find not only answers but the deepest questions of all. At the end of our exploration, magnetars stand before us not only as astrophysical objects, but as teachers. They are rare, fleeting, and violent, yet in their short lives they illuminate truths that stretch from the smallest particles to the largest scales of the cosmos. They are stars compressed to the size of a city, bound by gravity so strong that a teaspoon of their matter outweighs mountains, wrapped in magnetic fields so intense that they warp atoms and bend light. And from this violence, they give us lessons about nature, about science, and about ourselves. The first lesson is that the universe exceeds imagination. When neutron stars were discovered in 1967, it seemed almost unthinkable that nature could compress a star into such density. Magnetars pushed this astonishment further, showing that some neutron stars were not only dense but also magnetic beyond comprehension. Their fields, a quadrillion times stronger than Earth's, redefine the limits of what is physically possible. They remind us that the cosmos is not constrained by human notions of reasonableness. It produces what the laws of physics allow, however strange that may be. The second lesson is about unity. To understand magnetars, we must draw from many fields: relativity to describe their gravity, quantum mechanics to explain neutron degeneracy, plasma physics to model their magnetospheres, nuclear theory to probe their interiors, and astrophysics to trace their births and deaths. No single branch is sufficient. Magnetars demand synthesis, forcing scientists to work across boundaries. They show that nature does not recognize divisions between disciplines. It is seamless, and our knowledge must be equally integrated to understand it. A third lesson lies in fragility and resilience. Magnetars demonstrate how even the strongest materials can fracture under stress. Their crusts, billions of times stronger than steel, crack under the pressure of shifting magnetic fields. These fractures unleash flares brighter than galaxies, energy compressed and then released in seconds. Yet the stars endure. They continue to spin, to pulse, to flare again. They remind us that breaking is not always an ending. Fragility and resilience coexist, not only in stars, but also in life. Another lesson is perspective. When the flare of 2004 from SGR 1806-20 disturbed Earth's ionosphere, it reminded us that our planet, with all its life and history, exists within a cosmos that is active, powerful, and unpredictable. We are not insulated from the universe. We are participants in it. Our survival depends not only on the steadiness of the sun, but also on the fortunate distances between us and objects like magnetars. Their danger emphasizes our luck, that life arose in a pocket of relative calm within a violent galaxy. Magnetars also teach humility. For all our technology and knowledge, we cannot predict their flares, cannot yet explain fully how their fields grow or decay, cannot see their interiors directly. Even with satellites orbiting Earth and radio telescopes mapping bursts from billions of light years away, magnetars keep their secrets. They remind us that science is never finished, that mystery is not a failure, but the engine of progress. Humility in the face of the unknown is not weakness but strength, for it keeps curiosity alive. They also show that destruction can be creative. Locally, their bursts sterilize worlds, strip atmospheres, and disrupt space environments. Yet on galactic scales, they shape the interstellar medium, injecting energy into clouds of gas, influencing how new stars form. Their possible roles in superluminous supernovae spread heavy elements across galaxies, seeding the material for planets and life. Magnetars embody the paradox that creation and destruction are intertwined, that violence can be generative. Rarity is another lesson. With only a few dozen known in our galaxy, magnetars are among the rarest of stellar remnants. Yet their importance is enormous. Each flare, each burst, each detection reshapes astrophysics. A single flare in 1979 revealed the first giant outburst. A single flare in 2004 altered Earth's atmosphere. A single fast radio burst in 2020 proved that magnetars can produce signals once thought inexplicable. Their rarity amplifies their significance, reminding us that sometimes the rarest phenomena reveal the deepest truths. Finally, magnetars teach us about time. Their lives are brief, measured in tens of thousands of years, nothing compared to the billions of years of ordinary stars. Yet in those short spans they shout across the universe, leaving records in data and memory that outlast them. Their brevity heightens their meaning, just as rare moments of human discovery can change knowledge for centuries. They remind us that significance is not measured by duration, but by impact. As we close, magnetars stand revealed as more than dangerous stars. They are lessons in scale, in unity, in fragility and resilience, in perspective, humility, creativity, rarity, and time. They are messengers, their bursts carrying not only energy, but also insight. They tell us that the universe is stranger than we imagine, more unified than we perceive, more violent, and more creative than we expect. They tell us that discovery is a dialogue, that the cosmos speaks in signals, and we answer with understanding. And so, even as magnetars fade, their voices endure. They fracture themselves, yet in doing so, they illuminate physics. They are violent, yet they teach. They are dangerous, yet they inspire. They are rare, yet they transform our view of the cosmos. Somewhere, even now, another magnetar may be preparing to erupt, to send a burst across light years. We may not know when or where, but we will be listening. And when the signal arrives, it will remind us once more that the universe is alive with extremes, and that even its most dangerous stars are also its greatest teachers. The universe is vast, but it is not silent. Across billions of light years, signals whisper and roar, born from the collapse of stars, the fusion of nuclei, the bending of space-time. Among them, the voices of magnetars are among the loudest. They do not speak often, but when they do, their cries echo across galaxies, in bursts of X-rays, in flashes of gamma radiation, in millisecond pulses of radio waves. They announce their presence. Each burst is both a danger and a gift, both a release of stored violence and a message that carries knowledge to those who listen. To study magnetars is to confront the limits of what can be known. They exist at scales beyond experience, magnetic fields that warp matter, densities that crush atoms, energies that stagger imagination. We measure them in numbers, but numbers can only approximate the enormity. To approach their truth, one must also feel them as sudden eruptions in the night sky, as disturbances rippling through Earth's ionosphere, as mysteries that resist easy explanation. They are not simply stars. They are boundary stones, marking the edges of physics, points where our theories stretch until they nearly break. And yet, even in their violence, they inspire. They show us that the universe is creative beyond comprehension, that out of destruction comes light, and out of collapse comes a laboratory of extremes. They remind us that human beings, small and fragile, can nevertheless reach across light years to touch their signals. We cannot visit magnetars, we cannot see them directly, but we can understand them. In that act of understanding lies one of humanity's greatest triumphs, the ability to turn distant violence into local knowledge, to transform danger into wisdom. Still, mysteries remain. Why do they flare when they do? Why do some neutron stars become magnetars, while others remain ordinary? How exactly do their magnetic fields twist and fracture? Are they the hidden engines behind the brightest explosions in the universe? And what other secrets lie within their dense cores, locked beyond the reach of light? These questions are not yet answered. Perhaps they never will be. But perhaps that is the point. Magnetars are not puzzles to be solved once and for all. They are ongoing conversations between humanity and the cosmos, reminders that wonder endures wherever knowledge meets its limits. As we gaze into the night sky, we see stars scattered like dust across infinity. Most shine quietly, their light steady and familiar. But somewhere, hidden in that vastness, a magnetar waits. Its surface strains under invisible pressures. Its magnetic field twists tighter. Its crust prepares to crack. In an instant, without warning, it will flare, releasing energy brighter than a billion suns. Its signal will race across space, and perhaps, millennia later, it will arrive here, brushing Earth with its echo. We will measure it, study it, marvel at it, and in doing so, we will hear once more the voice of the most magnetic stars in the universe. In the end, the story of magnetars is a story of extremes, of violence turned into understanding, of rare stars that shape entire fields of science. But it is also a story of mystery, for even as we learn more, they recede further into the unknown. They are dangerous, yes, but they are also guides, reminders that the cosmos is greater, stranger, and more astonishing than we will ever fully know. And so, we listen. Somewhere in the dark, a magnetar is speaking.